Hello, Professor Simmons here. This video reviews a couple of ways of testing for whether a series converges or diverges. We'll be using these methods during the class, particularly in the section on separation of variables in spherical coordinates. Now, there are many different ways of testing whether a series converges. What differs among the methods? Well, typically, how easy the method is to use, whether there are any restrictions on when it applies, and the amount of information you get from the method. Obviously, you would like to find a method that's really easy, that applies everywhere, and that gives you all the information you want. Unfortunately, you can't always get all of those things in one package. We'll look at a couple of different useful methods, and we will use the harmonic series to check how these different methods work, because the harmonic series is the one that applied back on the very first day of the course when we built up a stack of rulers, if you will recall. The harmonic series, H, is the sum of terms that look like 1 over n, where n is a positive integer, and we showed that you could apply the integral test, converting the sum into a simple integral, and that showed that the harmonic series diverges as n goes to infinity. So we know the answer for the harmonic series. Now let's see what different tests will tell us about the harmonic series. That will let us see how well these other tests work and when they work. The first test that we will look at is called the ratio test. So let's apply the ratio test to some general series that is the sum of a bunch of terms b sub n. To apply the ratio test, you first make a ratio that is the absolute value of the next term divided by the current term that you're looking at. Now, this precise ratio that you've built is not exactly what you want. What you need to do is take the limit of that ratio as n goes to infinity, so you're looking out way at the far end of the series. We call that limit simply rho, whereas rho sub n related to particular terms in the series. The ratio test says that your original series will converge if this rho is less than 1, and the series will diverge if rho is greater than 1. But if rho is exactly equal to 1, you are out of luck, and the ratio test will not tell you anything. Let's try it on the harmonic series. For the harmonic series, our ratio rho sub n, well, all the numbers are positive, so we don't need to worry about the absolute value. Rho sub n is the next term over the current one, so that's n over n plus 1. And to think about what that would look like as n goes to infinity, it will be useful to write that as 1 over 1 plus 1 over n. Looking at it in that form, we see rho sub n is less than 1 because the denominator is always greater than the numerator, so we get hopeful. But remember, this is not what matters. What matters is rho, which is the limit as n goes to infinity of rho sub n, and that unfortunately is equal to 1. The ratio test is not powerful enough to tell us whether the harmonic series converges. It's easy to apply, and it works. It is easy to apply, and in principle you could try applying it to many different series, but it doesn't always give you an answer. Let's try a different method on the next slide. This one is called Gauss's test. Let's start again. Our series is a sum over a number of terms u sub n. Gauss's test, and I should note that the Arfken and Weber book talks more about this in Chapter 5, Section 2. Gauss's test doesn't always apply. It applies under certain circumstances. So it applies if each term in the series, u sub n, is positive, for all finite n at least. And also if the ratio of the current term over the next term can be written in the following form: 1 plus some number h divided by n plus a function b of n divided by n squared, where b is a bounded function of n as n goes to infinity. So as n goes to infinity, this function b can't become infinite itself. It has to be bounded by some finite value. So we have several restrictions here. Gauss's test only works if this restriction and if this restriction are met. Under that restricted set of circumstances, Gauss's test is very informative. It tells you that the series converges if that number h is greater than 1, but it diverges if h is less than or equal to 1. So it covers all cases of what h could be and gives you a definite answer. However, if some of the u sub n's are negative for finite n, you're out of luck. Or if you couldn't write this ratio in this very particular form, you're out of luck. Let's try it on the harmonic series. Well, for the harmonic series, we form the ratio. First we check, are the u sub n's always positive? Yes, the harmonic series involves only positive numbers. Now for the harmonic series, the ratio u sub n over u sub n plus 1 is just equal to n plus 1 over n. And we can write that as 1 plus 1 over n plus, well, we don't need a 1 over n squared term. So it's as though we had a b of n that was equal to 0. And 0 is pretty bounded. So this condition is met. And we notice that, in fact, our h is simply 1. Well, h less than equal to 1 tells us that our series diverges. So Gauss's test doesn't apply to every series, but it does work for the harmonic series and is powerful enough to tell us the series diverges. We'll look at some other cases of applying the ratio test and Gauss's test in class. That's all.